Thank you, ma'am. Before the commencement of today's program, I would like to give brief introduction about our college. Guru Nanak Education Society, Nagpur. Education Society, there are 3 colleges. Guru Nanak Institute of Engineering and Technology, GNIET. Guru Nanak Institute of Technology, GNIT. And Guru Nanak Institute of Hospitality Management and Catering Services, GNIHMCS, are such prestigious and well-established institutes in Nagpur. GNIT is one of the most nurtured branches of GNES, which is working with a mission of spreading engineering and management education among the students who belongs to rural areas. Now, I request Professor Rajendra Bombe sir, Vice Principal GNIET, to encourage us with his few words.
Good morning, Secretary, Indian Association of Radiation Protection, Convener and Speaker of today's program. Eminent speakers, Dr. V. Natarajan, ex-Professor BARC, Shri Sanjay Patil, Dr. Vijay Pavade, co-convener and assistant professor LITU Nagpur, Professor Sadab Gohar, Madam, HOD SH and co-convener, all deans, HODs of various department, teaching and non-teaching staff, and my dear student. Today we have gathered here for one-day workshop on beneficial effects of radiation technology and Indian Nuclear Energy Program. Radiation is used in medicines, academics and industry, as well as for generating electricity. In addition, radiation has useful applications in areas such as agriculture, archaeology, space exploration, law enforcement, geology and many others. This workshop is aimed to explore the beneficial effects of radiation technology. I appreciate the efforts of ASH department in organizing this workshop and hope all participants will be benefited from this workshop. Thank you.
Thank you so much, sir. Now, I would like to give brief introduction about today's chief guest, Dr. Sheshandri Murli sir. Sir is a retired scientist from Bhabha Atomic Research Center, BARC, BARC, Mumbai. Sir has been a specialist trainer in science and mathematics for students of secondary level, higher secondary level, graduation level and post-graduation level. Sir has a lot of passion for motivating students who are future leaders, decision makers to take science stream for their research career and applications of science in engineering cum technology for their individual and our overall national growth. Dr. Murli sir has been awarded both national level and international level for the scientific research work. Sir also a recipient of Meritorious Operational Health Physicist Award, few DAE Group Achievements Award and awards from the Defense Ministry for the Nuclear Strategic Work Program for India. Presently, Dr. Murli sir is training Radiation Safety Officers, RSO, serving at various private institutions where radiation technology has applications in medical, industrial, agriculture and academic fields of work. Indian Association for Radiation Protection, IARP, promotes beneficial applications and uses of radiation technology. Now, presently, Dr. Murli sir is the Honorary Secretary of IARP Resource Team, and also sir visits in self-finance manner in various educational institutes, universities and promotes the Indian Nuclear Energy Program cum beneficial applications of radiation technology. Various colleges in Mumbai, Navi Mumbai, various districts of Maharashtra as well as all over India, Sir has been visited by resource team of IIRP to deliver lectures on scientific research, career opportunities for students. During the one-day IIRP workshop on beneficial applications of radiation technology and Indian nuclear energy program. So, I would like to request Honorable Professor Rajendra Bombay Sir, Vice Principal GNIET, to felicitate today's chief guest, Dr. Sheshandri Murli Sir, Secretary IIRP, by giving shawl and shriffle. Sir. Now, I would like to request Dr. Sheshandri Murli Sir to give us brief introduction about IIRP activities and workshop. Please, sir.
Good morning.
Good morning, sir.
Dr. Hemant Hajre, who is in absentia, and Professor Rajendra Bombay, Dr. Vijay Pavade, the coordinator of this program, Professor Sadaf Kauhar, deans of various departments of this institution, my dear colleagues from IIRP, and dear students, most of you are gathered here to listen to this lectures, demonstration, and decide about your career opportunities in the future. So, good morning to you all. Indian Association for Radiation Protection is a non-government organization with specialists in nuclear energy field, safety, radiation safety field. We are propagating the beneficial effects of radiation technology, Indian nuclear energy program, especially to the younger generation. Thereby, either they will be taking up job opportunities, research opportunities, or if they have some motto, drive to supply some material in Indian nuclear energy program as industrialists are. So then we are trying to reach out to the younger generation and to the academic faculty members. Thereby they will be able to decide and tune their program for Indian nuclear energy programs applications in their field of work. IIRP conducts this sort of programs at university level, college level on request from the respective institutions. It is structured as a one-day program with capability to sense radiation. So we need to resort to detectors, detection, and then radiation safety. Normally there is a myth, there is a general beneficial effects of in modern way of life. We have in academic applications, research applications, in industry, in medical, in security, in water purification, and a variety of other fields. Even the recent Chandrayaan and even the Aditya, where they needed the power source, radioactive sources have used. We are talking about greenhouse effect, thereby to come out of this global warming scenario, we need to have a green, environmental friendly energy resource. Nuclear energy program exactly fits in the bill without pollution, without causing global warming releases. Nuclear energy can be the energy reactors which can be taken to urban tier 2 cities, etc. in supplying the needs of energy. So these type of nuclear energy program being the immediate requirement, you, the students, need to understand and need to decide about your career opportunities for your growth as well for the national impetus. So in that context, we need to give some sort of initial inputs. Thereby you will be able to decide, you will be able to act, and you will be able to take it up further in your career. So with that idea, IIRP reaches out to younger lot. Younger lot, those who are in the age of 20, 22, they have got a bigger dilemma and they have got a bigger challenge also. You are going to have to compete with machines, with these machines which are likely to be faster than you, so your efficiency has to be slightly enhanced. Thereby in the cutting edge you will be able to go ahead. So in that case, when you need to choose a proper area, proper direction in your career, we need to give you options. In that context also, we are reaching out to children who are the decision makers in the near future. Thereby they will be able to opt a clear cut idea for an environmental friendly manner to take it further. IIRP otherwise is conducting for academicians, for say researchers, on a periodic basis, conferences, workshops, team meetings, either team meetings, etc. once in a year or so, conferences, national, international. Recently we had conducted international conference in the month of February 2023 and likely to have national conference in 2024 October or 2025 January, February. So this is done to share our growing trends in radiation safety, radiation detection, in instrumentation and the regulatory aspects. So researchers, academicians can take part in IIRP activities. Besides, we have got a quarterly journal publishing our own work in paper form, which will give you the recent trend in research in this radiation safety, environmental safety aspects. So I would request you to be in the larger members of larger family IIRP. Thereby radiation safety can be understood, environmental safety can be further propagated, as you are going to live for a greater period in this environment which needs to be pollution free. Coming to today's workshop, we will be providing you these whatever presentations we will be making in non-editable form, so you can get some idea for your future projects, future study related things. And even if you are likely to take it up further in your career, that also is an option open. With that, I thank the organizers, the venue, for inviting us, giving us an opportunity to interact with you all, younger minds, and then hopefully we will be able to convince you to take this pollution-free technology for your futuristic either academic or research or industrial applications point of view. Thank you.
Thank you so much, sir, for enlightening us with your valuable words. Now, I would like to request Professor Sadaf Gohar ma'am to give vote of thanks.
A very good morning to all.
Good morning.
We shall be starting with the insightful and enriching one-day workshop on the beneficial effect of radiation, technology and Indian nuclear program energy. Very soon, but before that, I, Professor Sadaf Gohar, HOD ASH and co-convener of the workshop, would like to conclude this inauguration ceremony with the vote of thanks. I extend my heartfelt gratitude on behalf of the organizing committee to each and everyone present over here, over today's experts, Dean, HODs, faculties and their participants. Today, workshop is culmination of dedication, efforts, collaboration and the unwavering support of all involved. First and foremost, our sincere thanks to Dr. Seshadri Murli sir, Secretary IARP, the convener of this workshop and the retired senior scientist from BARC. His wealth of knowledge will give you the way that truly reveal into the essential aspects of radiation technology and the Indian nuclear energy program. A special acknowledgement to the Dr. Natarajan, member IARP and ex-professor BARC, whose meticulous follow-up and guidance play a vital role in the seamless organization of this workshop. His commitment to the cause has been invaluable. Heartfelt appreciation to the Shri Sanjay Shankar Patil, a member of IARP and coordinator on behalf of the IARP, for his contribution and dedication to ensuring the success of this event totally. Our sincere gratitude extend to Dr. Rajendra Bhumbe, Vice Principal GNIET, for his exceptional support and pivotal role in the execution of this workshop. His commitment to academic excellence has been truly commendable. A special note of thanks to Dr. Hemant Hazare, the Principal GNIET, and Honorable Sardarni Tanpreet Kaur Tuli, Secretary GNES, Honorable Sardar Nonit Singh Ji Tuli, Chairman GNES, for their continuous encouragement and support. A heartfelt thank you to Dr. Vijay Paude, co-convener of this workshop and Assistant Professor LITU. His support has been instrumental in making this event successful. Last but not least, a heartfelt thank you to all the dedicated ASH faculties, all the teaching and non-teaching staff whose hard work and commitment have been crucial and surely make this workshop success. Thank you. Thank you.
Thank you.
Thank you so much, ma'am. Now, I would like to request all the students and dignitaries present over here kindly stand in the honor of National Anthem.
जन गण मन अधिनायक जय हे भारत भाग्य विधाता पंजाब सिंध गुजरात मराठा द्राविड उत्कल बंगा विंध्य हिमाचल यमुना गंगा उच्चल जलधि तरंगा तव शुभ नामे जागे तव शुभ आशीष मागे गाहे तव जय गाथा जन गण मंगल दायक जय हे भारत भाग्य विधाता जय हे जय हे जय हे जय 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 हे
भारत माता की
जय
वंदे
मातरम
एवढं माझ्याकडे तो ऑनलाईन कोण किती जण ऑनलाईन बोलून राहिले.
Now we are entering in the first technical session of today's workshop. The chair for the first session is Dr. V. Natarajan sir. I would like to give brief introduction about Dr. V. Natarajan sir.
कितान
Sir has done PhD from University of Mumbai in 1990 and topic for his PhD is track level spectroscopic studies of actinized doped solids. Sir has done postdoctorate research at National Taiwan University, Taipei, in luminance in inorganic vandates and silicates, and advanced training in EDXRF from Israel. Dr. Natarajan sir was a former head in spectroscopy section and scientist at radiochemistry division in Bal, Mumbai, and retired professor in Homi Bhabha National Institute, Mumbai. Sir is a former adjunct professor at Institute of Advanced Research, Gandhinagar, Gujarat, and currently Sir is Honorable Professor at Neelkanth Shinde College of Arts and Science, Bhadravati, Maharashtra. Sir has been published 196 papers in national and international journals and 220 plus papers in national symposia journals. Sir has published 2 books chapters in book. Now I would like to request Dr. V. Natarajan sir to start the session. Please sir.
कवर काढावं लागतील कवर काढावं लागते एवढं आहे एवढं जास्त ते बी पबजी खेळत मोबाईलवर.
Thank you for the introduction. Slideshow.
चमन मी हे जर झालं.
Thank you for kind introduction and thank you organizers, Professor Rajendra, Bombay, and Secretary, National Institute of Engineering and Technology. The first you would have read during your plus 2 level. You might have read. It is a kind of pushing up your memory. Okay.
एवढा हालते कोण
Go to next slide.
स्टार्ट करणार.
Then go to next slide. See, now we come to the basic concept. What is atom? What is nucleus? This is all you have studied in 12th level. This is all you have studied at 12th level. Just I am going to introduce once again, atom, nucleus, protons, electrons, and other things. Go to next slide. Okay. I just like Professor Murali mentioned, radiation is a thing which is surrounding us all. Ionizing particular lecture. We will be talking about the effect of ionizing radiation. Okay, like alpha particle radiation and radiation, like gamma rays, X-rays, alpha particle, beta particle. Okay, next go to it. See, these are the scientists. You must be aware of these two. One is Henry Becquerel, who discovered radioactivity from uranium-bearing minerals. Okay, and second is from Madame Marie Curie, who worked with radioactive. She discovered radium, the radioactive isotope. Radium element was discovered by her, and both of them have received Nobel Prize. And I think Marie Curie had got 2 Nobel Prize. I do know 2 Prize. Radium. She had, because those days they were not knowing how dangerous it is, radioactivity. So she got cancer in the end. Okay. because he was not working with proper protection. He was separating radio from radioactive mineral. But Nobel Prize was given because he gave the lead to everybody. Otherwise, we would not have known about radio. Go to next one. Okay, now we come to the concept atom. No, what is atom? What is nucleus? Every atom. Let us say hydrogen atom or sodium atom. Any atom as outside nucleus, which will contain protons and neutrons. Protons are positively charged particle. Neutrons are neutral particles. These two will be there in the nucleus. Atom, electrons are orbiting around this nucleus. Atom has orbits where electrons will be revolving around the nucleus. So then the protons and neutrons are roughly, they have same number and atomic weight. These concepts you have been introduced, but just try to recollect. For example, you see here that let us go to that one where X, A is at the top, what is mentioned is mass number, at the bottom what is there is atomic number. That is atomic number is nothing but number of charges, number of protons in an atom or number of electrons in an atom, both will be equal. So one of the number of, in general, number of positive or negative charges, that gives the atomic number, and the atomic mass number is total mass. Usually it is equal to number of protons and number of neutrons. Roughly it will be equal to number of protons, number of neutrons. Okay. Then for example, you see here, this is carbon, where mass number is 12, atomic number is 6. It means it is having 6 protons, 6 electrons, and 12 mass number means 6 protons and 6 neutrons it will have, which will give it 12 mass number. Electron mass is negligible, so the number of proton, number of neutron together will give the mass number. Go to next slide. Okay, this is the order of masses of the particle. Proton, you see how much it is, 10 power minus 31 kg, the order of 10 power minus 31. And the neutron, you see, very close. Neutron is slightly bigger than proton. While the electron, you see, it is very less. It will be 1 by 1840 of that proton. So usually we can consider it negligible to the first upright. There is one more quantity called positron, which is we will discuss in the coming. It will be there. It is a particle which is similar to electron, but it has same mass, but it will have positive charge. Usually it is not existing in atom, but it will be created while radiation is interacting. Okay, go to next one. Next slide, please. Next slide. Okay, there are many other nuclear particles. Last 30 years, these all, if you study nuclear physics as your elective, will come across so many other particles. Just to introduce to you, I am giving this thing: antiproton, antineutron, and free neutron is possible. Neutrino, antineutrino. Neutrino is a small particle with zero mass and negligible mass, very small mass. Negligible means close to zero. And you have meson, which is mass in between proton and electron. There are 3 types of meson: mu, gamma, and kappa meson, and hyperons, which are larger particles, larger than protons, and their charge can plus or minus. Why these are all, we are not going to discuss today. They are all short-lived. They are all, only during experiment they are discovered. They are very short-lived. They are not existing, but they are existing for very short time. When people during experiment they are discovered these many particles. But what are stable thing we are discussing? Protons, neutrons. To radioactive. All of you know thorium is a radioactive mineral. Okay, and thorium is a radioactive mineral. What is radioactivity means? The element is unstable. It is emitting either alpha particle or beta particle, and sometimes in addition to this, it can emit gamma rays also. Okay, go to next one. Next slide, please. See, okay, why radioactivity is occurring? Radioactivity is occurring when elements normally, when you start with Z 1 to 20, number of protons and number of neutrons will be equal if they balance very well. then charge is increased further. That is what is called atomic number. That is atomic number. So or charge of the atom. So if that increases beyond 20, the number of protons and number of neutrons ratio, neutrons increase. Actually, it will go to 1.5 compared to a proton. Like if it is 40, that is 40. Protons may be 40, while neutrons can be 60 for the stability purpose. Okay, you see, this is a kind of curve. You can see, initially you will see is very close, 1 to 1. This is number of proton, number of neutron. Okay. You leave it linear up to where we say Z40. Okay. This 40 and later it increases. The number of neutrons required is more because the electronic repulsion between protons they are very strong. So compensate, you require more number of neutral particles. So number of neutrons increase. So beyond Z equal to 82, okay, Z is 82, the proton-proton repulsion become very high, uncontrollable, and under such circumstances, the atomic nucleus, it emits some particle. By emitting, it gets a stable state, it attains stability by emitting a particle and loses some energy, and then it is attaining stability. So that's why it is radioactive. Radioactivity is mainly due to proton-proton repulsion becoming very high when the Z atomic number is very high. Okay. So you can see there are some other points which are not high like that. Okay. Odd even is more stable. Even will be very stable. Okay. Even stable is there is a reason they will be occurring in paired state in nuclear shell. Just like atomic shell, nuclear shells are also there. Anyhow, this much is sufficient for this course. Go to next one. Next are there. Nature, 1700 radioactive nucleides are there. Okay, every element has at least one radioactive isotope will be there. For light element, that is proton to neutron ratio is one I already told you. Go to next one. It will increase for every element. This also I told you that plot is there, no? Okay, go next one. That Gratin 83, all isotopes will be radioactive. Go to next one. Now radiation and radioactivity. Okay, by definition, same thing. Radiation is by definition energy in the form of electromagnetic waves or particulate matter. Particulate matter is particle, charged particle, beta or alpha, traveling in air. Okay, radioactivity already we explained. Go to next slide. So there are radiation, every red alert, as I told you, radiation is many things, starting with ultraviolet, infrared, and then you have microwave, radio wave, everything. All these are radiation. But what is more dangerous is gamma rays and X-rays, because they have the property to, they can ionize with their energy, they ionize the atoms of the body. So they are more dangerous. We have to take safety precautions when you handle with gamma rays and X-ray. Okay. So non-ionizing radiation, even this light, this is non-radiation. But non-ionizing radiation. For all electromagnetic radiation, forget about alpha and beta, all electromagnetic radiation, energy is given by E equal to HDO. H is Planck energy. For gamma is the equation, even for radio waves is the equation. So what is the difference? Energy is different for each radiation. And gamma and X-ray have a lot of energy which can ionize our body tissue and create damage. That is why they are harmful. Okay, go to next slide. And there are different kind of radiation. Naturally also there are radiation processes. Okay, one sort is primordial. Primordial means we have in rock, we have uranium, thorium. In rock, no, some parts per billion uranium, thorium can be there. Here is already there. Okay, so from here radioactive isotope will come by decay from uranium and thorium. One particular radioactive isotope is a radon, which is a gas. It will be present entire world, any part of the world. If you go, if there is a rock, there will be some radioactivity. Okay, it will be very small amount. And then you have cosmic rays. In the atmosphere, you have cosmic rays. They collide with air, nitrogen, oxygen in the air. This also will give you radioactivity. Go to next. Then anthropogenic radioactivity. This is because of man-made radioisotope which are used in industry and medicine. And then these are the different things. Dr. Murli will be talking more about it. These are some applications. Medicine, security, medical research, industry. All different type of radiation are used. Okay. Go to next. So radon, as I mentioned, in this natural radiation. To 22 3.84 days. Half-life. What is half-life? I will come to that next. Go to next one. Okay, sources of background radiation. Okay, background radiation I told two sources. One is rocks, another is cosmic rays. Third one is whatever food we eat, in that there will be potassium 40. Whatever food we eat, we have potassium. The potassium has radioactive isotope potassium 40, which will be in small amount, it will be present in food. So whatever food we consume or in that we will have potassium 40. Like the carbon 14 also can be there in our food. Okay. Because they are all small fraction. Why they are not harming us? They are all in very small fraction. Maybe 10 power minus 12 gram, 7 gram in that level. Okay. Then go to next. Then okay. These are, you can divide in the radioactive two electron. Helium atom is having atomic number 2, mass number 4. Means 2 proton, 2 neutron, 2 electron. To knock out 2 electron, whatever is left is helium nucleus. That is alpha particle. Alpha particle is nothing but helium nucleus. It is having 2 positive charge. But its mass number is 4. It is basically, that is why we represent it as, you see, alpha particle is represented as 4. Mass number is 4. Then the charge is 2. That is how it is represented. After decay of a radioactive isotope, it emits alpha. The product will have, see, this is Z. Alpha has 2 charge, so product will have Z minus 2, while mass will decrease by 4. Okay, the product. This is called parent, this is called daughter. Okay, parent and daughter. Go to next slide. Beta particle. See, then beta particle, there are 2, beta minus and beta plus. Beta minus is nothing but electron. Electron will moving electron with energy. Beta plus is a positron, it is called. Radioactive decay, sometimes you get beta plus, which is the similar to electron. Mass number will be similar, 1 by 1840 of the proton, but charge will be positive. Okay. So beta plus, the right side you see, right side you see when X, a nuclide is emitting a beta particle, what you get is one neutron is converted into proton and electron. Okay. And then electron. That is why charge is increasing. They are increasing the charge. You get electron, the proton increases the charge of the daughter product. And you have another particle called antineutrino. Okay, anyhow, their mass is less and not, just for completion's sake, their lifetime is not high. It is there. Okay. Similarly, beta is positron. Positron means just like electron, the mass will be 1 by 1840 and charge will be positive charge, 1 plus 1. So you have positron emission. When positron is emitted, the daughter nuclide Z will decrease, Z minus 1, opposite of earlier one, and mass will remain the same. Okay. And you have one more process called electron capture. It is similar to positron, where proton from the nucleus will capture one orbital electron. The effect will be similar to the positron. Go to next one. magnetic charge. What is the product? Product is protactinium 234. Mass number remains same. Charge increases by 1. Okay. Charge increases by 1. So protactinium. That is the thing. If it is similar way, positron emission, you go to boron 8. Boron is having atomic number 5. Mass number 8. It is emitting positron. It becomes charge increases by 1. Opposite of this. So it becomes beryllium 4. Z less by 1. And mass number is same. Because why mass number is same? Because electron and or positron, their mass is very small, 1 by 1840 of proton. So we consider it as 0. So we say mass number is same. Okay, go to next one. Now vacancy. So one from higher orbital jumps to k electron. When higher orbital jumps to k electron, that vacancy that is filled. But there is an energy difference, which will be coming as X-rays. So X-rays origin is orbital. Okay, gamma rays origin is nucleus. Okay, that difference is there. Here example is here, nucleus, cobalt, Cc. Cobalt emits beta and then it is converted into nickel. Then before coming to ground state, it is emitting 2 gamma rays. Okay, this is what is used for medical purposes, this particular cobalt system. Okay, and X-rays, I told you, orbital, and there will be a difference in energy. Gamma rays have higher energy always. They have the energy around 1 to 100 keV. Gamma rays will have energy from maybe 10 to 5, 6,000, 7,000 MeV. Can have up to 10 MeV also, gamma ray. Go to the next one. You are able to hear, no?
Yes, sir.
Find her.
Light one.
Laser light.
Now, in summary, it is, whatever I have told you, it is summary. Alpha is basically helium nucleus, and beta particle is an electron, negatively charged electron. Positron is positively. Neutron is a neutral particle. Neutron is basically charge, mass number 1, charge is 0. It is neutral particle. Then gamma ray, you know. Okay, go to the next one. Next slide. AB, same thing repeated. Go to the next one. Okay, here stopping power of different radiation. Important. Alpha particle can be stopped easily. Range is very less. Range मतलब कितना दूर जाएगा? वो alpha particle को एक पेपर से आप उसको stop कर सकते हैं. When beta particle को आपको aluminium और perspex चाहिए, plastic और aluminium रखेंगे तो beta particle को stop कर सकते हैं, उसका cut off कर सकते हैं, उसका energy stop कर सकते हैं. Gamma ray के लिए आपको heavy element चाहिए. Normally lead tungsten इस तरह का heavy element आपको इस्तेमाल करना पड़ेगा. Gamma rays को stop करने के लिए you have to use heavy element like lead or tungsten or what is called depleted uranium. इस तरह का heavy element की इस्तेमाल जरूरत पड़ेगी. Go to next जाइए. ये कुछ नहीं है. Whatever radiation मैंने बताया same thing, मतलब diagram दिया है. मतलब everywhere all over the world common आम आदमी को radiation dose मिलता है. It is not because of atomic energy establishment. Nature में ही radiation है. Go to next one. Okay, ये भी same thing, cosmic ray मैं जो बताया उसी का. Okay, what is the order of dose? Some figure है. We'll come to that. Next, go to next one. Half life. Radioactivity का एक concept मैंने नहीं बताया, पहले ही बताना चाहिए. I have told why the nucleus are not stable. Each radionuclide has a characteristic property what is called half-life. Half-life मतलब you take cobalt 60. Cobalt 60 है, its half-life is 5.3 year बोलते हैं, 5.3 year. इसका मतलब क्या है? आप 1000 atom of cobalt लीजिए, after 5.3 year it will become half. 1000 atom जो है 500 atom decay हो जाएगा cobalt का. तो activity 500. Same way you take anything, uranium 238 you take. U238. If you take 1000 atom U238, वो 500 एटम होने के लिए ऑफ डीके होने के लिए 10 power 9 years जरूरत है. 10 power 9 years मतलब बहुत लॉन्ग ऑफ लाइफ. ऑफ लाइफ जो है इट इज वेरी कैरेक्टरिस्टिक फॉर ईच आइसोटोप. हर आइसोटोप के लिए डिफरेंट है. वो मतलब हर रेडियो आइसोटोप के लिए डिफरेंट है. सो इट इज लाइक ए फिंगरप्रिंट. आपको पता चलेगा अगर आप एक सोर्स है उसमें से स्पेक्ट्रम रिकॉर्ड करते हैं, उसमें 4-5 पीक मिल रहा है, कौन सा पीक कौन सा रेडियो न्यूक्लियेट से आता है करके यू कैन फाइंड आउट. गो टू नेक्स्ट वन. ऑफ लाइफ. सो ऑफ लाइफ इज ए कैरेक्टरिस्टिक प्रॉपर्टी ऑफ ए न्यूक्लियेट, रेडियो न्यूक्लियेट. ठीक है. ओके, मैंने जो बताया कार्बन 14 डीकेस टू नाइट्रोजन 14, 238 डीकेस टू क्लोरीन 234. ऑफ लाइफ. ओके, गो. तरह का पूरा डीके. ओके, लेड. सो इसमें 8 अल्फा 6 बीटा एक्स है. ये जो प्रोडक्ट विच इज ऑन द सरफेस यहाँ भी रहेगा. ये जो है रेडियम रेडॉन 222 ये यहाँ भी रह सकता है स्मॉल क्वांटिटी में एनीवेयर, क्योंकि वो सरफेस आएगा, जमीन से आएगा. ओके, नाउ वी हैव टू गो टू नेक्स्ट स्लाइड. रेडिएशन यूनिट ये इम्पोर्टेंट है. मतलब रेडिएशन के बारे में आप अभी जान गए हैं. रेडिएशन को कैसा मेजर करना है, यूनिट क्या है. गो टू नेक्स्ट वन. ये जो है देयर आर 3 थिंग्स. वन इज रेडियो एक्टिविटी, किस तरह का, हाउ रेडियो एक्टिविटी व्हाट इज द यूनिट. सेकंड इज एक्सपोजर and then is exposure in air, then exposure of persons, then observed dose in body में observed dose. ऐसा 4 they are there. And beta and gamma radiation are considered equally damaging. Okay, well alpha will consider greater damage. Okay, go to next one. Okay, we come to the units. Now radioactivity का unit है becquerel. One becquerel is one disintegration per second, 1 dps, that is 1 becquerel, and that is very small unit. So higher unit है 1 curie. 1 curie is 3.7 into 10 power 10 disintegration per second. And there is one more. So normally curie is a big unit, becquerel is a very small unit. So the in between the megabecquerel whatever. 1 curie is 37 megabecquerel. Mega means 10 power 6. Okay, mega means 10 power 6, giga means 10 power 9 becquerel, like that. Okay, curie. What is curie? Why earlier they named curie? Because when Madam Curie discovered radium, whatever was the activity of 1 gram of radium 226 was defined as curie. That was 3.7 into 10 power 10 disintegration per second. ठीक है. Go to next one. ठीक है. Radiation doses का unit है एक्सपोजर यूनिट. एयर में गामा एंड एक्सरे के लिए एक्सपोजर यूनिट है रंजन और कूलम पर किलोग्राम. एंड ऑब्जर्व्ड रेडिएशन डोज को वी से ग्रे और रेड इज ऑफ 1 kilogram if you observe 1 joule, then it is called 1 gray. Actually, it is a big unit. Body के लिए milligray is a small unit will be used. So 1 gray means 1 kilogram of body tissue will observe 1 joule of radiation energy. Then it becomes 1 gray dose. Okay. Same way, biological dose. Biological dose is keyword. What is the difference? We will come to that. Go to next one. Next slide. Exposure. Exposure is basically exposure concept जो है कितना ionization produced because of radiation, that all gamma or X-ray, कितना ionization produce, वो concept है. Okay, here मतलब how much charge. So exposure is total number ion, positive or negative per unit mass of. इनका effect different है. Alpha, beta, gamma, neutron सबका range अलग. Alpha short range है, but it will produce बहुत heavy ionization produce होगा. तो मोर डैमेजिंग होगा. बीटा एंड गामा आयनाइजेशन रफली सिमिलर है. सो उसका जो एक्चुअली एनी दे आर कंसिडर्ड ऑलमोस्ट सिमिलर. ओके, सो व्हाट इज देयर इक्विवेलेंट डोज के लिए ऑब्जर्व्ड डोज को यू हैव टू मल्टीप्लाई बाय रेडिएशन वेटिंग फैक्टर करके एक है, यू हैव टू मल्टीप्लाई फॉर दैट. So X-ray and gamma ray is considered 1. This is a standard. X-ray gamma is 1. Alpha 20 times more damaging. So उसको you have to multiply 20. And neutron के लिए depending on energy radiation weighting factor change होगा. So जो भी observed dose है उसको if you multiply by this radiation weighting factor, we will get equivalent dose. Whatever is observed in the body, equivalent dose is the one which will tell you how much damage will be produced. So this unit is CGS में ram है, rad का equivalent ram है, and SI unit में gray का equivalent sievert है. 1 sievert is 100 gram. Just like 1 gray is 100 rad, 1 sievert is 100 gram. Go to the right. ऑर्गन में डैमेज नहीं प्रोड्यूस करेगा, किसी ऑर्गन में ज़्यादा प्रोड्यूस करेगा, किसी में कम प्रोड्यूस करेगा, उसके लिए एक फैक्टर है. We have to multiply and sum up. So that is called effective dose. मतलब equivalent dose जो है उसको टिश्यू वेटिंग. Suppose thyroid को I am applying cancer में thyroid को they are applying source. Then you have to apply equivalent dose जो भी है उसको thyroid के लिए 0.12 कुछ factor है, उससे multiply करेगा, you will know how much energy is deposited. Okay, why they are important? In cancer therapy, you should know how much dose you have to give for the tumor in the tumor. So your calculations are very important. Okay, go to next. Commuted dose. Okay, suppose sometime go through nose, inhale or inject, मुंह से जा सकता है. Then the definition is different. How much accumulated dose for 50 years? It is called commuted dose. It depends on what ingest radioactive particle, how much it will stay and all that. Like air में से it will normal public के लिए इतना important नहीं है, but those working with the radiation field for them it is better. तो अंदर जाता है, मुंह में जाता है और lungs से जाता है. Okay, go to next. Okay, there are radiation effect को दो define करता है, deterministic and stochastic effect. Deterministic effect में क्या है? There is a threshold. थ्रेशोल्ड मतलब इतना डोज के नीचे कुछ नहीं होगा, इसके ऊपर थोड़ा डेंजरस है. लाइक 0.1 ओके. थ्रेशोल्ड मतलब as I told there is a dose 0.1 gray. 0.1 gray is the threshold dose for human common मतलब रेडिएशन वर्कर्स के लिए. 0.1 gray 100 मिलीग्राम, उसके ऊपर some effect will happen, छोटा इफेक्ट होगा. So that is threshold. And threshold stochastic मतलब it is a probability. Any dose में कुछ भी dose में हो सकता है. जैसा मैं बताता हूँ. Suppose 2 vehicles are coming. I cross the road. Accident हो सकता है. Okay, that is you can say threshold. 2 vehicle आ रहा है, मुझे देख के जाना. तीसरा क्या है? I am crossing, कोई हाई स्पीड में आके मुझे नॉक करता है. वो stochastic मतलब probability. वो कम है, नॉर्मली नहीं होगा बट हो सकता है. सो डिटर्मिनिस्टिक मतलब 2 गाड़ी आ रहा है, मुझे देख के क्रॉस करना है, मेरा डोज उससे कम होना चाहिए रेडिएशन. ओके, देन there are many things. So there are radiation protection is important. That's why these are all taught to you. Deterministic means a particular dose is measured for each radiation worker. And common man also, common public also, every year they take out some this thing. And okay, go to next. So radiation protection is very important. Okay, सब नहीं है. Go to next.